Right, in this video, we're going to talk about Chapter 6, dealing with normal probability distribution. So this starts Chapter 6. So we're going to talk about the standard normal distribution, and then we'll go into applications of the normal distribution, and also we'll deal with the central limit theorem. So those sections pretty much deal with the normal probability distribution. So in section 6.1, we'll look at the standard normal distribution. And out of that section, we're going to describe the characteristics of a standard normal distribution. Also, we'll find the probability of some range of z values in a standard normal distribution and find z-scores corresponding to regions under the curve representing a standard normal distribution. Okay, so the standard normal distribution has three properties. One of them is this: the graph of the standard normal distribution is always bell-shaped. Okay, if you recall, it does start with a low number, and then it increases up to a maximum number, and then starts decreasing to one or two low numbers. That would be a standard normal distribution, or a bell-shaped curve. Number two, the standard normal distribution has a mean equal to 0. So here we're going to be using the Greek letter mu. And that's going to be equal to 0. And number three, the standard normal distribution has a standard deviation equal to 1. So here, the Greek letter sigma is the population standard deviation, equaling to 1. All right, now let's talk about normal distributions. So here in this section, we'll develop the skill to find the area or probabilities of relative frequencies corresponding to various regions under the graph of the standard normal distribution. And in addition, we'll find z-scores that correspond to the areas under the graph. Okay. Now, there are infinitely many different normal distributions depending upon the values used for the mean and the standard deviation. We begin with an introduction to this general family of normal distributions. So here's the definition of a normal distribution. If a continuous random variable has a distribution with a graph that is symmetric and bell-shaped, we say that it has a normal distribution. And this is the formula for the normal distribution. Now, in this course, we will not be using that formula for the normal distribution. So basically, we're just going to be using the normal curve, and also we're going to be using tables, as I will explain later in this video. Let's talk about the uniform distribution. We begin with the uniform distribution, which allows us to see the following two very important properties. Number one is that the area under the graph of a probability distribution is equal to 1. And number two, there is a correspondence between area and probability, or relative frequency. So some probabilities can be found by identifying the corresponding areas in the graph. Okay. And here's the definition of a uniform distribution. It is, okay, a continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape. So let me pull this page up so that way you can see the rectangular shape. And we call this a density curve. That's the graph of a continuous probability distribution. And the density curve has to have these two requirements. The total area under the curve must be equal to 1. And every point on the curve must have a vertical height that is 0 or greater. So here you can see underneath this density curve, which is of course a rectangular shape, the area, that's the space that's inside this region, has to be equal to 1. The points on the curve must have a vertical height that is 0 or greater. So that's your height. If you recall, when you find the area of a rectangle, it's always going to be the length of the rectangle multiplied by the height. And of course, that's your length here, which is going to be, in this case, for example, the waiting time in minutes. And then the height represents the probability of X. Okay. So that's just a basic introduction of what a uniform distribution is. Now, the one we're going to talk about is the standard normal distribution. Now, keep in mind, because the density curve of a normal distribution has a complicated bell shape, it is more difficult to find the areas. However, the basic principle remains the same, that there is a correspondence between area and probability. So keep in mind the area underneath the curve represents probability. Okay. So for the standard normal distribution, by definition, it is a normal distribution with the parameters of the mean, the population mean equaling to 0, and sigma, the population standard deviation, equals to 1. The total area under its density curve is equal to 1. Okay. Now, on the next page, you'll see an illustration of what that normal curve is. Okay. The vertical axis, as you can see, is the z-score. This area that's underneath this normal curve is always going to be equal to 1. Okay. Now, keep in mind, it's not easy to manually find the areas, but we have 2 other relative easy ways of finding those areas. One would be the use of technology, and the second is the use of table A-2, which is a standard normal distribution table. Okay, so let me pull up this normal distribution table that we have here. This is what it looks like, and it's actually 2 pages in your handout at the end of these notes. Okay, this one is for negative z-scores, because this goes from 0.0 all the way up to negative 3.49, actually from 0.01 negative all the way up to negative 3.49. The second page is for positive z-scores from 0.00 all the way up to 3.49. And we're going to be using this to help us find our probabilities here shortly. And here is how we find the probabilities when given z-scores. Okay. Because you will be given z-scores and you want to find their corresponding probabilities here. So here we can find the areas or probabilities for many different regions by using a TI-83 or 84 plus calculator or computer software such as StatDisk, Minitab, Excel, or StatCrunch, or we can also use table A-2 in Appendix A, or at the end of the notes that you see here. The use of technology is strongly recommended because they generally give more accurate results. So if we're using table A-2, which is what we'll do in this video, here it is important that you do understand these points. In number 1, it says here table A-2 is designed only for the standard normal distribution, which has a mean of 0 and a standard deviation of 1. Table A-2 is on 2 pages with the left page for negative z-scores and the right page for positive z-scores. So those 2 sheets that I showed you, that first sheet is for negative z-scores, and then the next one is for positive z-scores. And number 3, each value in the body of the table is a cumulative area from the left up to a vertical boundary above a specific z-score. That's going to be very important because if you look at the table itself, it tells you cumulative area from the left. So if you drew a normal curve and they ask for the cumulative area from the right, you have to do something different here because these values in the body of the table, and this is the body of the table, by the way, represents cumulative area from the left. And number 4, when working with a graph, avoid confusion between z-scores and areas. And here's the definition of a z-score and the area. Z-score is the distance along the horizontal scale of the standard normal distribution. Refer to the leftmost column and top row of table A-2. So that normal curve that I showed you right here, this horizontal axis, that is your z-score. The area is this space right here underneath that curve. And that represents the region under the curve, and you refer to the values in the body of table A-2. So don't get z-scores and areas confused. And number 5, the part of the z-score denoting hundreds, which is the second digit after the decimal point, is found across the top row of table A-2. So if you look here, that top row represents the digits in the hundreds place, which is the second number after the decimal point. The digits here on the far left, that represents the number in front of the decimal point and a number after the decimal point. Okay. So that's very important that you understand how to read this particular table. In fact, let's look at some examples of just that. Let's say I want to find the area to the left of 2.56. The area to the left of 2.56, okay? And part B, we're finding the area to the left of negative 1.74. So here's where we use table A-2. And as 2.56 is on the side where it says positive z-scores. Okay. Now, I'm going to have to find 2.5, which is this number on the left-hand side where my finger is at. 2.5. And then the 0.06, that's the last digit after the 2.5. That's on this top row up here where I have 0.06 here. So now I'm going to read across from 2.5 and down like this. And notice that decimal value is 0.9948. Again, here's 2.5 and here's 0.06. Read across and then down. You'll see that it's 0.9948. That represents the area to the left. So the area to the left of that would be 0.9996. Okay. Okay, 2.5 and then 0.06. I'm sorry, it's 0.9948. 0.9948. So that's how we read that table. So again, 2.5, and then 0.06 is right here. Read across and down, 0.9948. Now, what about negative 1.74? I want to find the area to the left of that. Here we got a negative, so that means I need to use a page that says negative z-scores. So we're going to find the negative 1.7 on the left-hand side. So here's negative 1.7 here, and then 0.04. That's the last digit in negative 1.74. Okay. Now I'm going to read across and down. That decimal value for negative 1.74 would be 0.0409. .0409. That represents the area to the left of negative 1.74. Okay. And if you like to, you can try to get more practice by coming up with additional z values here, and then try to come up with to find those corresponding z-scores. I mean, those probability values for those z-scores. Okay. All right, next is just formats for finding a normal distribution. When you're finding the cumulative area from the left, that's this shaded area here, we can use Table A-2 or StatDisk or Minitab, Excel, or StatCrunch to help us do that. And what about the area between two boundaries, like this one, the lower and the upper? Now, you can use the TI-83 or 84 plus calculator or StatCrunch to help you find the area between the two boundaries. Okay. On this page at the very bottom, this is just a portion of Table A-2 that you see here that we just talked about. Again, make sure when you're using this, it's the cumulative area to the left. Okay. Now, on the next page is how to find those probabilities. So here, the area corresponding to the region between two z-scores can be found by finding the difference between two areas found in A-2, Table A-2. So here, the probabilities can be expressed with the following notation. The first one is this: the probability that some z value is between A and B. That's similar to this right here. You have a lower and an upper boundary. So in this case, that denotes the probability that the z-score is between A and B. And the way you do that, you find the area corresponding to the region between the two specific z-scores and find the difference between the two areas found in A-2, Table A-2. So here we find the cumulative area to the left of B and the cumulative area to the left of A and subtract the two. Make sure you subtract the larger probability minus the smaller probability, because keep in mind, probabilities cannot be negative. Now here, if we have a probability that some z value is greater than A, that means we're looking for the area to the right of A. Then in this case, we have to find the cumulative area from the left of A and subtract that from 1. Since the area underneath the curve is going to be 1. So it's got to be 1 minus the cumulative area on the left of A. So if you've got a z greater than A, that's when you do 1 minus the cumulative area from the left of A. Because in the table, it does give you probability values that are representing the cumulative area from the left. You want the area on the right, so that's why you do 1 minus the cumulative area from the left. And the probability that Z is less than A is automatically going to be the cumulative area to the left of A. Reason for that is because the table does say cumulative area from the left. That's the one we want. And less than A means the area to the left of that. Okay, now let's look at a few examples of this to get our feet wet. In this first example, we're going to find the area of the shaded region. And the graph depicts the standard normal distribution with the mean equal to 0 and the standard deviation equal to 1. So here, our Z is 0.99. We want this area to the left. So that means we're looking for the probability that our Z, and it's shaded to the left, so the inequality symbol has to be less than 0.99. Okay? And 0.99 is a positive value, so we need to look at the table or the page for a normal distribution that says positive C-scores. Now let's find 0.99. Well, the first part of that is going to be 0.9, and then 0.09 is way over here. So if I go across and come down, you're going to see that it is 0.839. That's 0.8369. Yeah, 0.8369. Okay, so okay, I'm sorry. Sometimes these tables are hard to read. 0.9 and then 0.09, that's 0.8389. Okay, 0.8389. So that means the probability that our Z value is less than 0.99 would be 0.8389. Okay. Okay, so again, to find 0.99, you look at 0.09 and then 0.09, go across and down, that's 0.8389. Okay. Okay, now on the next page is another example. This time we're looking for the cumulative area on the right-hand side. You see that shaded area on the right side? That's the area we're trying to find. And this graph also depicts the standard normal distribution of bone density scores with a mean of 0 and a standard deviation of 1. And in this case, your Z value is negative 0.96. Oh, and it's negative. So we're finding the probability that Z is shaded to the right means greater than negative 0.96. So we need the page that says negative Z-scores. That's what we need, the page that says negative Z-scores. And here we go. So here we need to find negative 0.9. I'm going to need to move this up because here's negative 0.9 where my finger is, and then 0.06 is right here. So negative 0.9, we go across and down. Now this does says 0.1685. 0.1685. However, that 0.1685 represents the cumulative area on the left side. That's going to be this area on the left. That's 0.1685. We don't want that. We want this shaded blue area on the right. So to do that, we have to do 1 minus the cumulative area from the left. And the 1 comes from the fact that the area underneath this curve is equal to 1. And we know the area to the left is 0.1685. So to find the shaded area on the right, we'll subtract 0.1685 from 1. And that would give us 0.8315. That will be this shaded area on the right. So that means the probability that our z value is greater than negative 0.96 would be 0.8315. Okay, here's the next example. Find the area of the shaded region and assume that this graph depicts a standard normal distribution of bone density scores with a mean of 0 and a standard deviation of 1. Okay, so now we got 2 z values here. We're finding the area in between those 2 boundaries here. Our z is negative 0.81. The other z value is positive 1.26. So I need the probability of z being being equal to negative 0.81. And I also need to find the probability that our z is equal to 1.26. And we can say less than because we're looking for the cumulative area on the left anyway. And then once we find those probabilities, we will subtract those 2 areas. Now it gives the area in between the 2. So let's start off with negative 0.81. And it's a negative z-score. So we need to go to negative z-scores here on this table. Find negative 0.8. And then 0.01, which is up here. That's the second column on this table where you got 0.01 and then negative 0.8 here. Come down and then go across. That would be 0.2090. So the area to the left of that is 0.2090. To the left of 0.81. That's this area to the left. This is the boundary of negative 0.081. And that area is 0.2090. And now for 1.26. Let's see, that's a positive, so we need to go to the table that says positive z-scores. So in this case, I need to find 1.2, which is right here, and then 0.06, which is this column here. Go across and come down. That's 0.8962. Okay. So for z less than 1.26, this probability will be 0.8962. All right, now that 0.8962 is going to be this area going all the way to the left. But going all the way to the left here and here, we're not concerned with that. We need the area in between those 2. That's where we do the subtraction here. So in this case, we're finding the probability that negative 0.81 is less than some z value and less than 1.26. In other words, the probability that our z value is between negative 0.81 and positive 1.26, we take that 0.8962 and subtract from it 0.2090. And keep in mind, the larger minus the smaller. If we did the smaller minus the larger, we'll get a negative number. Probability values are never going to be negative. So it's 0.8962 minus 2.090. That would give us 0.6782. 6872. So the final answer there would be the probability that our Z value is between negative 0.81 and positive 1.26 would be 0.6872. Okay. Here's example 4. Assume that a randomly selected subject is given a bone density test. Those test scores are normally distributed with a mean of 0 and a standard deviation of 1. Find the probability that a given score is less than 1.89 and draw a sketch of the region. Okay. Now I've already have a illustration on a normal distribution from -3 to 3. Okay, so here we're finding the probability that our Z is less than, that's the symbol for less than, 1.89. So I'm going to say on this right here, 1.89 is somewhere over here, getting closer to 2. Let's say this is 1.89. I'm going to draw my boundary right here for 1.89. And the shaded region, less than, I have to shade to the left, because less than, you always shade to the left. If it was greater than, then you shade to the right. So this is the shaded region right here that I'm trying to find. So here I use table A-2, and it is a positive 1.89. So we use the positive z-scores page. We're going to find 1.8, which is here, and then 0.09, which is up here. Go across, all the way across and all the way down, you'll see that we come up with 0.9706. So this shaded area to the left is what we were looking for, 0.9706. Okay, now go ahead. So this is all the way out here, so it'll be 0.9706. Okay. All right, next example would be this. Assume that a randomly selected subject is given a bone density test. Those test scores are normally distributed with a mean of 0 and a standard deviation of 1. Draw a graph and find the probability of a bone density test score greater than 0.45. So now we're looking for the probability that the Z value is going to be greater than 0.45. And that's the symbol for greater than. So let's find 0.5 here on this bell-shaped curve. Let's say that it'll be about right here. Boundary line for that. Greater than means that we need to shade to the right of 0.45. So here I'm shading to the right of 0.45. So that's the area we're looking for there. Now, for 0.45, we're going to use our Z table, use the page that says positive Z scores. So here I'm going to find 0.04 and then 0.05. We read across and down. Now keep in mind, this does say 0.6736, but that's for the cumulative area on the left, not the right, the cumulative area on the left. So this area on the left of 0.45 would be 0.6736. We're not looking for that area that's on the left. We're looking for the shaded area that's on the right. So here we're going to do 1 minus 0.6736. Again, the 1 comes from the fact that the area underneath the entire normal curve is 1. That's one of the properties of a normal distribution. So if I subtract 0.6736 from 1, I will get an answer of 0.3264. So here the probability that a bone density test score is greater than 0.45 if the subject is randomly selected, that would be 0.3264. Okay. Here's another example. Assume that thermometer readings are normally distributed with a mean of 0 degrees Celsius and a standard deviation of 1 degree Celsius. A thermometer is randomly selected and tested. For the case below, draw a sketch and find the probability of the reading. And the given values are in Celsius degrees. So here we're looking for a probability of getting a reading between 1.00 and 1.75. Okay, so here we're going to mark up the 1 right here. We got that. So there's a boundary line for that. 1.75 is about 3/4 of the way between 1 and 2. So I'm going to say 1.75 is about right here. So here's 1.75, and we got the 1 here. Draw a boundary line for that. And I'm going to shade the area in between those two. Those are the two we're trying to find. So this is the shaded area we're trying to find here. All right, so now let's use our table A-2. And we're going to start with the probability that Z is less than 1.00. Using table A-2, we're going to find 1.0. That's right here. And then 0.00 is here. Read across and down, you'll see that your value there is 0.8413. So the probability of getting a Z value less than 1.00 will be 0.8413. Now that 0.8413 is this area to the left. And now for 1.75, we're going to find its probability. So going back to table A-2, we're going to find 1.7, which is right here, and then 0.05 is right here. When we read across and down, you'll see that it is 0.9599. .9599. All right, now that 0.9599 represents this area to the left, all the way to the left. We don't want that. We want the area in between. So that means we need to subtract those two areas here. So the probability that 1.00 is less than X and less than 1.75, meaning that the probability of, that should be Z, not X. The probability that our Z value is between 1.00 and 1.75, we just subtract the larger probability of 0.9599 minus the smaller of the two probabilities, 0.8413. And that difference will be 0.1186. That's this shaded area in between 1.00 and 1.75. So to answer the question, the probability of getting a thermometer reading between 1.00 and 1.75 degrees Celsius would be 0.1186. Okay. Here's another example of finding probabilities here. Given z-scores, find the indicated area under the curve in other standard normal distribution, then convert it to a percentage and fill in the blank. And it says here about blank percent of the area between z equal -1 and z equal +1, or within 1 standard deviation of the mean. Okay, so let's mark off -1. That's this. And +1. That's this. So we're looking for the area in between those two z values, -1 and 1. So I'm shading that area. Okay, so now let's find the probability that our z is less than -1.00 and the probability that z is less than +1.00. Starting with -1.00, that's a negative z-score, by the way. So let's go to the page that says negative z-scores. Here we go. Find -1.0, that's down here. And then 0, 0 is that first column. Go across and down, you'll see that it's going to be 0.1587. So that represents the probability of z less than 1.00, which is, of course, this area to the left. And then for 1.00, I think we did this in the last example, but I'll do it again to show you how to find 1.00 in the table. And in this case here, here's 1.0. And we have to look on the page that says positive z-score. So 1.0 is here, 0.00 is there. Read across and down, you'll see 0.8413. So here's one right here. From here all the way to the left, that's the 0.8413. That's the cumulative area to the left of that. We don't want that. We want the area that's in between these two. So that's where we have to subtract. So here's the probability that our z value is between -1.0 and +1.00 would be subtracting 0.8413 minus 0.1587. If you subtract those, you'll end up with 0.6826. Now, they want this as a percent. So if you recall, when you convert a decimal to a percent, you can do one of two things. One, you can move the decimal point 2 places to the right and add the percent sign, or you can take that decimal value and multiply by 100. Well, if I move this over 2 places to the right, it will be 68.26%. So about 68.26% of the area is in between z equal -1 and z equal +1, or within 1 standard deviation of the mean. If you recall back when we did the normal distribution, when we were talking about the percentage of values, of data values that are within 1 standard deviation, or within 2 standard deviations, or within 3 standard deviations of the mean. Here, that's part of that normal curve. And this is the case where 68% approximately 68% of the data values are within one standard deviation of the mean. And in this case, it's exactly 68.26%. Okay. So this first part dealt with finding a probability when you're given z values here. Now we're going to go the other way around. Let's say you were given the known area. We know the area underneath the curve, and we want to find the z value that corresponds to that area. So in many cases, we may be given a known area or probability. We need to find the corresponding z-score. So here we're going to use the following procedure. Number one, you want to draw a bell-shaped curve and identify the region under the curve that corresponds to the given probability. If that region is not a cumulative region from the left, then you're going to work instead with a known region that is a cumulative region from the left. Sometimes you'll be given a cumulative region that is on the right side. But if you're going to use table A-2, those values are only for the cumulative area that's on the left. So you got to do 1 minus whatever the cumulative area on the right is to get the cumulative area on the left. And then you'll use table A-2. Okay, and number two, you'll use technology or table A-2 to find the z-score. With table A-2, you want to use the cumulative area from the left. Locate the closest probability in the body of the table, and then identify your corresponding z-score. Now, there are special cases here. So if a z-score is negative 1.645, that cumulative area to the left would be 0.9500, or negative 1.645. The cumulative area from the left would be 0.0500. And 2.575 for a z-score would give you a cumulative area from the left of 0.9950. And negative 2.575 would give you a cumulative area from the left of 0.0050. Now, anything above 3.49, the cumulative area from the left would be automatically 0.9999, and below negative 3.49, the cumulative area from the left would be 0.0001. And if you notice in this table A-2, somewhere in the middle, you'll see an asterisk. If you follow that asterisk all the way down to here, if you have an area of 0.9500, that z value will be 1.645, or 0.9950, then it's 2.575 for your z value. And the same holds true for the negative z-scores. There's the asterisk. If you follow that asterisk all the way down, for 0.0500, the z-score is negative 1.645. And then 0.0050 for the area, that z value will be negative 2.575. Okay, those are just some special cases that you'll have. Now, the question is, which side do you use? The negative z-score page or the positive z-score page? Here's a hint. If the probability value that you're dealing with is less than 0.500, or 5,000, I should say, 0.5000, you're going to use the page that says negative z-scores. Or if the probability value is at least 0.5000, use the positive z-score page. That should help. Now let's look at some examples of this, like example 8. Here we're going to find the indicated z-score. The graph depicts a standard normal distribution with a mean of 0 and a standard deviation of 1. So here our area Notice that number is on the left-hand side, 0.8925. Okay, that's this area on the left side. So now we need our z value. We can find that in table A-2. And notice that 0.8925 is bigger than 0.5. So we have to use the page that says positive z-scores. Okay. So we need to look inside the body of the table, just like here's the body of the table, to find 0.8925. And guess what? I found it right here. 0.8925 is in the body of the table. Now I'm going to read from the left of that and up top to find the z value. So in this case, 0.8925 corresponds to a z value of 1.2 and then 0.04. So I'll take 1.2 plus 0.04. That would, and if I add those together, I'm going to get a z value of 1.24. That is the z value that corresponds to the area to the left of 0.8925. Okay, here's another example. Example 9. Find the indicated z-score, and this graph depicts the standard normal distribution with a mean of 0 and a standard deviation of 1. And that area to the left that we have is 0.3015. Notice that 0.3015 is less than 0.5. So we need to look at the page that says negative z-scores. Okay, so here's negative z-scores because 0.3015 is less than 0.5. We need to find 0.3015. And here it is, 0.3015. And we need to read from the left and from the top. 0.3015 to the left of that is negative 0.5. The column that 0.3015 is in is going to be 0.02. Okay. So our z is this. I'm going to put a negative in front, and that was negative 0.5, negative 0.0, no, negative 0.5, and then plus 0.02, because that's the column that 0.3015 was in. I'll show you again. Here's 0.3015 right here. To the left of that is negative 0.5. The column that is in is 0.02. So this would be negative 0.5, and then plus 0.02 would be negative 0.52. So negative 0.52 is the z value for 0.3015. Now suppose you had something like this. Here we want to find the indicated z-score. And the graph depicts the standard normal distribution with a mean of 0 and a standard deviation of 1. And we want to find its probability. All right, notice we got the area to the right. If we're going to use table A-2 to help us, we need to find the area on the left-hand side. That's going to be this unshaded area on the left-hand side. So let's start by finding the area to the left. Now the area underneath the normal curve is going to be 1. So we got to do 1 minus that area to the right, which is, of course, 0.9292. So 1 minus 0.9292 would be 0.0706. 0.08. It's this value that we're going to look for in the table. So in this case here, that 0.0708 is less than 0.5. We need to look under the page for negative z-scores. So here's the page for negative z-scores. Let's see, let's find 0.0708. And that's right here, 0.0708. Find the row that it's in and the column that it's in. We see in the row is negative 1.4. The column that is in is 0.07. So the z is going to be negative, and I'm putting this in parentheses, 1.4, and then plus 0.07. So my z is going to be negative, and if I add 1.4 to 0.07, that would be negative 1.47. That's the z value that corresponds to the area to the left. And this right here would represent the probability that our z is greater than, since it's shaded to the right, of negative 1.47, which is of course 0.9292. So that's how you read that table. When you're given an area to the right, you have to first do 1 minus that area to the right to get the area on the left side. Here's another example of that. Here's example 11. Here we're going to find the indicator z-score. The graph depicts a standard normal distribution with a mean of 0 and the standard deviation of 1. Now notice you're given an area to the right, and in this case it's 0.2090. So the first thing you have to do there is find the area to the left if you're going to use table A-2, which is that standard normal distribution table. So we got to do 1 minus this area to the right, which is 0.2090. So if I subtract 0.2090 from 1, I'm going to get 0.7910. So that's this area to the left right here. .7090. And it's that 0.7910. .7910. So I'm going to use that number, that decimal value. I'll be looking for that in table A-2. Now 0.7910 is bigger than 0.5, so I need to go to the page where it says positive z values or positive z-scores and find out what that z-score is going to be. Okay. So let's find 0.7910 or 0.7910, and here it is. So to the left of that would be 0.8. The column that is in is 0.01. So our z is going to be 0.8 plus 0.01, which would end up being 0.81. So the corresponding z value for this curve will be 0.81. Okay, now this could be the probability that your z is, since it's shaded to the right, you have to use greater than 0.81. That would be equal to that 0.2090. Okay. All right. Now, next we'll look at this one. It's just dealing with a mean of 0 and a standard deviation of 1. Assume that the readings on the temperatures are normally distributed with a mean of 0 and a standard deviation of 1.00 degrees Celsius. A thermometer is randomly selected and tested. Draw a sketch and find the temperature reading corresponding to P87, which is the 87th percentile. This is the temperature reading separating the bottom 87% from the top 13%. So here's a normal curve. Now notice that the axis is not labeled. The horizontal axis is not labeled. Let's say 87%, that's most of this normal curve. So that would mean that the Z will have to be somewhere over here. In this area to the left, that's the bottom 87%. Now 87% as a decimal is going to be 0.87. And if you didn't know that, you can drop the percent sign and divide by 100. 87% would be 0.87 as a decimal. Now I'm carrying this out to two more decimal places because my table is to 4 decimal places. So I want this to 4 decimal places as well. 87% as a decimal to 4 decimal places will be 0.8700. Is this value that I'm going to try to find for my corresponding Z value here. Now we're not going to find 0.8700 in the table exactly, but we're going to try to find a decimal that's closer to 8700. And of course, it is greater than 0.5, so that means we need to use a page that says positive Z-scores, which is this. So here we're going to look for a value that is closest to 8700, 0.8700. I'm going to use this one right here where it says 0.8708. That's closest to 8700 by 8. Now, if I use 0.8686, that wouldn't work because that's less than 14. So I want to use the one that's closest. So I'm going to use the 0.8708. Find the corresponding Z value for that. And that will be 1.1 and then 0.03. The 1.1 is on the left. The 0.03 is the column that it's in. So if I add 1.1 to 0.03, this will be 1.13. So the corresponding Z value will be 1.13. And that number, that Z value, represents the 87th percentile. That's the Z value that separates the bottom 87% from the top 13%. Okay, here's another example. Assume that a randomly selected subject is given a bone density test. Bone density test scores are normally distributed with a mean of 0 and a standard deviation of 1. Draw a graph and find P6, which is the 6th percentile. This is the bone density score separating the bottom 6% from the top 94%. So I know it's a small percent. So I'm going to say the Z is over here to the left of 0. And here I'm going to shade in that 6%, which is this right here. And 6% as a decimal, by the way, is 0.06. And I'm going to carry this out to 2 more decimal places. So that area underneath the curve is 0.0600. Now we're going to find a probability value that's closest to 0.0600, because you're not going to find that exactly in the table. And since this is less than 0.5, we need to use a page that says negative z-scores. Okay, so here's negative z-scores here. We need to find the value that's close to 0.0600. Okay, I'm gonna use this one, 0.0606. That's closest to 0.0600. And I'm gonna read to the left and read on the top above. So 0.0606 has a corresponding z-value of negative 1.5 and 0.05. So my z would be negative, and here I'm going to say 1.5 plus 0.05. That would give us a negative. Add these two together, you'll get 1.55. So here, negative 1.55 is the z-value that separates the bottom 6% from the top 94%. Or we can say negative 1.55 represents the bone density score for the 6th percentile. Okay. And here's another example. Assume that the readings on the thermometers are normally distributed with a mean of 0 and a standard deviation of 1.00 degrees Celsius. Assume 3.3% of the temperatures are rejected because they have readings that are too high, and another 3.3% are rejected because they have readings that are too low. Draw a sketch and find the two readings that are cutoff values separating the rejected thermometers from the others. Okay, so we know 3.3% are rejected because they're too high. So we know we got a z-value over here somewhere. And 3.3%, another 3.3% are rejected because their readings are too low. I'm going to call the one on the left Z1 and the one on the right Z2. And of course, the shaded area that I'm going to put in, say in green. This represents 3.3% of the thermometer being rejected because the readings are too low. If we do 3.3% as a decimal, and I'll go and show you. If I do 3.3, divide that by 100, because percent means per 100, that's 0.033. Now I'm going to add a 0 behind it. 0.033, 0 behind it. This also represents 3.3% of the thermometers being rejected because their readings are too high. That's also 0.0330. And we're going to find Z1 and Z2. Let's start off with Z1. That's the area to the left of that. That's going to be easy to find. Since this is less than 0.5, we're going to use a page that says negative z-scores and find a decimal value that's closest to it. I'm going to use this one that says 0.0329 right here. That's about 1/10,000 of a point less than that. And the corresponding z-value for that 0.0329 will be negative 1.8 and then 0.04. So that's going to be negative, and then 1.8, and then I'm going to add to it the 0.04. And that would be negative 1.84. So this is negative 1.84 over here. Now, if I know this, I can easily find Z2. The reason for that is this. These two numbers are symmetric to each other. They're the same. This bell-shaped curve is symmetric. That means the left side has a mirror image of the right side. So here, Z1 would be the opposite of Z2. So Z1 is negative 1.84. Then Z2 will have to just be the opposite of that, which is, in this case, 1.84. Now, of course, if you wanted to, you can go through the motions of subtracting 1 minus 0.0330 and then look on the page that says positive z-scores, which is, of course, 0.9669670, and try to find a decimal value close to that. And you'll see that it's going to be 1.84. So in this case here, if it have a reading that's less than 1.84 or a reading greater than 1.84, then those thermometers would be rejected. Okay. All right, the last thing in section 6.1 is critical values. Now, when we get into hypothesis testing, we're going to be talking about what critical values are in more detail, and also in confidence intervals, which is chapter 7. Here's a definition. For a standard normal distribution of critical value is a z-score on the borderline separating those z-scores that are significantly low or significantly high. Critical value is going to be a z-score on the borderline separating the z-scores that are significantly high or significantly low. And here's the notation. The expression z sub alpha, that denotes the z-score with an area of alpha to its right. And this is the Greek letter alpha. Looks like a fish. Now, there is a caution that you need to be aware of. When using table A-2 for finding the area of z sub alpha for a particular value of alpha, notice that alpha is the area to the right of z of alpha, but table A-2 lists the cumulative area to the left of a given z-score. So to find the value of z sub alpha by using the table, you're going to resolve that conflict by using the value of 1 minus alpha. So like in this case here, let's say I want to find the indicated critical value in example 15, and that's z of 0.07. Now go ahead and write this out, z sub 0.07. So in this case here, this represents the area to the right because of the definition. It denotes a z-score with an area of alpha to its right. So here's the area to the right, and that's the 0.07. Okay. This right here is alpha equals to 0.07. Okay. If we use table A-2, which we will, we need to know this area to the left. We need to know what that is first. The area to the right, area to the left is this. 1 minus this area to the right, which is 0.07. So if I subtract 0.07 from 1, I'm going to get 0.9. 3. And let's do this. Extend this out to two more decimal places, because the table uses 4 decimal places. So it'll be 0.9300. That's going to be the area to the left. So now we're going to use table A-2. That is 0.9300 is bigger than 0.5. So we have to use a page that says positive z-scores, which is this. And we're going to find a value that's close to 0.9300. Let's see, in this case, 0.9306, which is right here. 0.9306 is closest to 0.9300. So to the left of that is 1.4. The column that is in is going to be 0.08. So here, z of 0.07 is 1.4 plus 0.08, which gives us 1.48. Okay. So that critical value that we were looking for z sub 0.07 would be 1.48. Okay. Now, I realize that this was a lengthy video because there's so much that I need to cover dealing with the standard normal distribution and how to use that table. So try to get as much practice as you can using the table, finding probabilities for z values, and also finding the corresponding z value for when you're given a known area. Okay, so that will complete this video on section 6.1 dealing with the standard normal distribution.